All right, so last time we were talking about using the exponential equation as a way to model exponential growth and decay. And then we also ended with these ideas called doubling time and half-life. So kind of intuitive concepts, doubling time, the amount of time it takes for something to double, and then half-life, the amount of time it takes for something to be cut in half. So let's look at some examples in Excel. We're going to start with example 9 here. And so it says that the number of cells in a tumor is doubling every 3 months, and it's going to begin with just one cell. How many cells in 3 years? So over here in Excel, we have our month and our number of cells. So our initial number of cells, we're not told, if you remember I mentioned, if you're not told a particular, like let's say starting year or starting time or something along those lines, starting month, then your default is going to be you start at time 0. That is your initial condition. And here initially there is one cell. Now, I don't want to extend my month by ones because I don't know what happens every month. I know what happens, looking back over here, what I know is what is happening every 3 months. So I want to count up by threes. So 3, 6, and so on. Then to create a quick list of numbers in Excel, remember this is where you can highlight 2 cells at once, hover in the lower right-hand corner, right over that little green square in the bottom right, hold down with your left mouse button and drag until you see that number that's kind of in the upper right here as I'm going down until you see it get to your desired number of 36. Now, over here in my number of cells column, we'll start with equals because we're going to tell it to do some math. And we want it to double. So we want to cell reference this initial starting quantity. So we're able to extend the spreadsheet. And we want to multiply that times 2 because we're doubling. And then we're going to hit enter. Now here you do not want to do what we did over here with that double highlight. That is only to create a quick list of numbers. I don't want it to count up by 1, 2, 3, 4. I don't want it to do that. Whenever you have typed in a formula with a cell reference like we've done here, you just go back to that one cell where your formula is, hover in the lower right-hand corner, and either click and drag or double click. Going all the way down to 36 months, we can see that there are, in 36 months, there would be 4,096 cells in that tumor. All right, let's look at the next one, example 10. So this is the kind of thing that is really all around us right now. It's not Ebola that we're talking about. We're talking right now, this is why I'm doing this video from my house, we're talking about the growth of coronavirus or COVID-19. But here we have an example that is about an outbreak of Ebola that occurred back in 2014. And this was an article from a headline in Time magazine that at that time the CDC was saying that the number of cases of Ebola could double every 20 days. If you're listening to the news at all, you are surrounded with these types of headlines and hearing them talk about, I mean, I hear it all the time. It's like, I wish I was teaching to emphasize this, but I'm hearing them talk about exponential growth, that the number of cases right now, hopefully this will change soon, but that the number of cases are currently growing exponentially. So we're going to model this situation. So this was number of cases in West Africa could double every 20 days if there was no intervention. This is why we're home right now, by the way, is we're intervening, hoping to flatten that curve of exponential growth that we're experiencing today with COVID-19. So let's start, for purposes of this model, we're going to start with just one case of Ebola, and then we're going to model what would happen roughly in a year, so about 360 days. So again, I didn't say a particular day or date or year, so the initial condition is always 0. And here I did say at 0, 1, so let's just start with one case. Again, I don't want to count up by 1, 2, 3, 4, 5 days because I don't know what's happening every day. What I know is what's happening every 20 days. So here we want to count up by 20s. So 20 and 40 and so on. And at some point you can say, oh, I can make Excel do this counting by double highlighting, hover over that green square, hold down with your left mouse button and extend. Go all the way until we get to 360, which is right here. Then we're going to go back up and do the exact same thing that we did in number 9. This is doubling time. So this is going to equal that initial value times 2. And then we're going to go to that formula. We're not double highlighting here. We have a formula with a cell reference, and then we just extend that column. So what we would see in about a year, if there was no intervention, there would have been approximately, the number of cases would have been 262,144. So we can see, and we're living today in a situation where this is why, and it says right here, if there was no intervention, this is why we intervene to try to curb the growth of these diseases. So that was in 1 year. If you want to, this is what a lot of these models are based on. If we wanted to, frighten ourselves even more, if things were just allowed to grow, without any intervention, we can see how fast the nature of doubling becomes frightening. So that's kind of a very important lesson that we're all living through today. All right, number 11. Now it says the current population of a threatened animal species is 950,000, but is thought to be declining with a half-life of 20 years. So we want to determine how many there'll be in 80 years and how long until the animal species could potentially become extinct. So again, the initial condition here, the initial year, we just start at time 0. It didn't say like in the year 1980 or something. It said just now. So current initial is at time 0, and there are 950,000. All right. Now, in this situation, I am told the half-life is 20 years. So again, I don't know what happens from 1 year to the next. Again, what I know is what is happening every 20, in this case, years. So once again, we double highlight to create, a quick list here. Now, initially, I only want to see what happens after 80 years, but eventually I want to see how long it's going to take, the population to become extinct. So I'm just going to extend, really far down, and we'll see if that's enough. All right, my population now, instead of doubling, we're going to take it in half. So we can either divide by 2 or multiply by 0.5. So we're going to start with our equals. So I'll reference that initial population, and then let's just kind of follow the layout in the notes. We're going to divide by 2. It would have been equivalent to multiply by 0.5, whatever seems most intuitive to you. And so in 20 years, again, just always kind of testing these for reasonableness. In 20 years, my population was cut in half. Go back to that one cell that you have your formula in. Do not double highlight here. Just fill from that one cell. And yeah, this looks good. I can see that every 20 years, my population's being cut in half and half and half. So the first question was, what would the population be in 80 years? So in 80 years, the population is going to be this 59,375. Okay, so that's what it would look like in 80 years. All right. Now, to think about when the population of this animal species might go extinct, well, initially we might think, well, extinct would be when there would be none of these animals left. But I get to a point here where I end up with fractional or decimal portions that are less than 1. So obviously you can't have less than 1 animal. So at 380 years, I had 1.8-ish. So maybe somewhere around 2. And then by 400 years, I'm less than 1. So mathematically speaking, we would say that we would go extinct after 400 years. But realistically speaking, this isn't going to behave purely according to the math. It probably would have happened before that. As we kind of think about maybe just the conditions, or what are the odds that they're continuing to reproduce at the same rate when there's such a small population in the wild. I'm sure there's biologists that could speak much more to maybe when they get down to very small numbers, they may decrease even more quickly after that. Maybe when you get to under 100 or under 30, the population goes from here to extinct in much more quickly. But mathematically speaking, we can say, 400 years. All right, so number 12, we're going to return to an example of having a shot of espresso with 64 milligrams of caffeine. And this time I'm asking the question, so it's a little different than what we've done before. Here, we're told that it's eliminated, and in this case at a rate of 11.5% per hour. And here I want us to determine the half-life. So unlike number 11, example 11, where I gave the half-life and we answered some questions, here we're going to start with a typical model like we did in previous sections, and we're going to determine the half-life. So here's what I know. I could start this one and say at 2 p.m. and so on, but I think I'm just going to start with this, again, initial time at 0. So here, 0 really represents 2 p.m. So I initially ingest 64, and what I know this time is what is happening each hour. So I'm back to counting by increments of 1 here, because I know what's happening each hour. So I'll double highlight, pull down, get some values here. Maybe I'll need more, we'll see. And then let's model this exponential decay. So this is going to equal, you have your two options, kind of your 1-term or your 2-term approach, whatever you like better. Kind of the 2-term approach would look like the initial value minus, because it is eliminated, 11.5% as a decimal, 0.115, or Excel does know a percent and what that means. You could say 11.5%, whatever you prefer. And then that times that percent of the initial quantity. So the initial quantity eliminated by 11.5% of that initial quantity. So this is kind of the percent decrease approach as opposed to the growth factor, the single term approach, whichever. We'll try to do a combination of the two. Go to that last cell and then double click just to fill that formula. So if I start with 64 milligrams, what I'm really looking for is I want to think about when 64 gets cut in half. So 64 divided by 2 would be 32. So I'm thinking about that 32 milligrams is going to occur somewhere between 5 and 6 hours. So at 5 hours, we have more than 32 milligrams. At 6 hours, we have less than 32 milligrams. So it would be somewhere in between our 5 and 6 hours. So using Excel to solve, this is precise enough. That's about as far as we're going to go with that. Okay, so this would be our half-life. I could ask a similar question and might in an activity where if it was something that was growing, I might ask what's the doubling time. So then you'd be looking for how long it takes some initial population to double. That's another way I could ask a question like similar to this, but on the doubling time side of things. All right, so we have, I think, just one last example here, example 13, and this one involves carbon-14 dating. And so it says the half-life of carbon-14 is about 5,730 years. So first of all, let's kind of think about that if we were to think of how we did other half-life problems. So we would model half-life by just, cutting that previous amount in half, and then we counted up by what the half-life was. Like if it was 20 years, we counted by increments of 20. All right, well, this would not do very well for us. We would not get very precise answers if we were counting up by increments of 5,730 years. I mean, my level of precision would be in 5 to 10,000 year increments, basically. So instead of working with that, here's the key. It translates to a decay rate of 1.202% every 100 years. So rather than cutting something in half for 5,730 year increments, we can decrease it by this percent, but we can count up then by 100-year increments, and then we'll have more precision in our answer. So this example, we're going to focus on the Dead Sea Scrolls. When they were found and tested, they contained about 78% of the normally occurring amount of carbon-14. So however scientists determine what should have been there, that I don't know. But when they tested them, they found out that they contained about 78% of what would have been there initially. So we don't know, we don't have initially there should have been 17 milligrams. We don't have a milligram. What we have is a percent of what should have been there. So our columns here, we have years and percent of carbon-14. So initially, when they were first created, those Dead Sea Scrolls, they had 100% of whatever amount of carbon-14 that should have been there, it was there. 100% of it was there to begin with. Then we're told what is happening every 100 years. So we're going to count up by hundreds. So we are going to double highlight, and we're going to then pull down, get into some of the thousands here, and we'll see if that does enough. And then what we're told is they are losing, so decaying, 1.202%. So a lot like just the decay situation that we did in the last example, just simply initial value minus percent decrease times initial value. That's essentially what we're going to do here with these carbon-14 problems. We're going to say, okay, this equals, and we're going to cell reference kind of where we start, minus, so trying to just kind of mimic that really similar structure that we had in the last example. So minus the 0.01202, so that's the 1.202% as a decimal. If you're a little nervous on something like that you might lose a decimal space or put in a zero that shouldn't be there or something, then just type it in like it is. Excel always will understand as long as you throw that percent sign on it. So this is always an option. And then it's this percent of that initial cell in B2. So initial value, it's decay, this percent of initial value, and then enter. So after 100 years, they would contain about 98.8% of what there should have been initially. So let's extend that one formula cell. We'll extend that down. And we are looking for the fact that they contain 78% when tested. So we want to look and see over here in Excel, when do they get to 78%? All right, well, here's where that would occur. So what we see is in 2,000 years, we have a little over 78%. In 2,100 years, we have a little under 78%. So these Dead Sea Scrolls are going to be somewhere between 2,000 and 2,100 years old. So somewhere between 2,000 and 2,100 years old. And so there's more current estimates that their dates are, and this pretty closely parallels what we found, but that they're dated to be from a time somewhere between 150 BC and 5 BC. But that's what we would get with our carbon-14 dating. There's other types of substances. Carbon-14 isn't the only one that's used to date artifacts, but it's probably the most common that we see in a lot of our examples. So we're not going to talk about the regression with an exponential model. I don't think it really comes up in any of your activities or assignments, especially right now, given our current situation. That's going to be something that we won't spend time talking about. In terms of this activity, I think I am going to, for my students anyway, if you have a different teacher, you may want to double check. I'm going to shorten my group activity 15 and just say, let's focus on 1 through 7 only. This isn't too bad of one. I'm just trying to shorten these group activities a little bit given our current situation. This would have been a lot like the carbon-14 one. It's just using a different substance called uranium-238, and it has a different decay model. It decays 7.41% every 500 million years. So this is for dating things extremely old. So this was a moon rock that I was going to have you look at here. So you will omit that one if you're my students, and you will just be doing 1 through 7 in group activity 15.